Today we're going to continue talking about Unit 2.5 in the periodic table. So having your periodic tables available to you at a moment's notice is always something beneficial. Comes down to today we'll talk a little bit about how some of the numbers on the periodic table matter. When we look at the comparison of the masses, protons and neutrons have essentially the same mass. As we can see here, the two masses of them are very similar. The electron is very small. Again, you can, and that's in comparison, and that's in AMU. So that would be when we look at say the atomic mass of hydrogen, you would see it's very close to 1, and it's almost very close to the atomic mass of a proton. That's because, well, hydrogen has just one proton. It also has an electron as well, but because the electron's mass is so small, it is pretty much negated out. To the point where we just ignore it. Protons and electrons are the only two subatomic particles that have a charge. We do have, again, those subatomic particles. They do have mass. Because they have a mass, they would be calculated in there. But for the atomic mass, is for the most part not negated. And since the electron is so small as well, we also negate that or ignore it essentially as well. The protons and the neutrons should also be noted that those are located in the nucleus, and the electrons are talking about what they're looking at or where are they located. That was a major focus of Unit 2, and it will also be information that is from that is the electron configurations, and the Bohr models are things that we will continue to work with and look at as well as we continue forward. So the atomic number, or the whole number that's on most periodic tables, is the atomic number. It is the number of protons, and that is the important thing. The atomic number is the number of protons. It can be the number of electrons, but remember from last unit that electrons can change. We can gain electrons, become an anion. It can lose electrons and become a cation. However, the number of protons defines what the element is. That is why the atomic number, the whole number, is the number of protons. It is important that those two are the same. Because the number of electrons can vary, we can no longer say the atomic number is the number of electrons. In a neutral atom, it will be. But now that atoms can gain or lose, we're going to need more information. And we'll get that as we move forward. The atomic mass number is the total number of protons and neutrons. Okay? And the atomic mass number is usually looking at that really long number that has a lot of decimal places. Those ones will also have be rounded for that reason to the nearest whole number to give us the atomic mass number. Because you can't have a half of a proton or half of a neutron. That doesn't work. Okay? So that gives us whole numbers of protons and neutrons. The reason why they are long decimal numbers is because they have the protons and neutrons have very small mass. When the number of neutrons can vary, and how that number is calculated, and it's called a weighted atomic average, and it's a weighted number, meaning the atoms that have more mass or are more abundant have more kind of pull on the actual mass that it has. So we'll get into that later, but for our purposes in using what's called nuclear symbol or atomic notation, those long numbers need to be shortened up, rounded up or down to the nearest whole number so that we can use that information. Nuclear symbols or atomic notation is a way to determine the number of protons based on the fact that you have the atomic number and the number of neutrons by being able to subtract 12 from 6 in this example here. What atomic notation or nuclear symbols go with is it also really helps us identify isotopes. And isotopes is where you have a different number of neutrons altogether. So the number of neutrons can also vary. And this is where I think sometimes some of the two terms can be very difficult to understand for students. We have ions when electrons are gained or lost, and now we have isotopes when neutrons can be gained or lost or vary. So really the only subatomic particle that never changes for an element is the number of protons. And that is, again, because that defines what the element is. As I said, isotopes, here would be the 3 isotopes for carbon. The most common one that we see is first carbon, is carbon-12. That's what we call it. It might not have an actual value or a mass of 12, but we call it carbon-12 because it rounds up or down to the whole number of 12. That allows us to indicate which carbon we're talking about when we're in mixed company. Say, are we talking about carbon-12 or carbon-14 or carbon-13? It's these isotopes that are very important to not just chemistry, but biology and microbiology, as they're trying to track where, say, a virus or a bacteria or cells are rotating through. It's these isotopes that they're able to add to it a certain isotope to an item, and it will float and go through your body as they can see and find out how it's interacting. Carbon-12 is a naturally occurring isotope. You have a certain amount of carbon isotopes, carbon-14. When you die, that amount of carbon-14 no longer is replenished. So and it starts decaying. You've probably maybe have talked about this in math class, where you would have had a exponential decay or rate of decay, and those graphs usually would look kind of like that. And you look at the half-life of a atom, and they're able to actually pinpoint how long a person has been decomposing or dead based on that. So archaeological evidence of certain how do they know something is that old? They use isotopes of carbon to do that as well. So let's think about something real quick here. Two atoms with the same atomic number but different mass numbers are called what? Don't answer. one moment. Just think about it. So when we look at this, we can see, obviously, mutants is not it. Isomers is a chemistry term. It's just not what we're going to use for this. Isotopes, the correct answer. And then symbiotes would be another science term, but we're not going to use that one in this one. And so we are good to go on that. So, determining the subatomic particles and nuclear symbol for the following. So I'm going to make this chart, and it's very similar to one that you may have seen in a, say, a Mastering Chemistry or some other homework. It's very commonly done for many different things. And so it will be very helpful, I think, for us to kind of, I'm just going to rewrite it all out as we kind of go through some of this. So I'm going to resize some things and then write out a little chart here. All right. So I have my examples there. I have my periodic table right there. And so I am going to make my chart, let's say strontium. We're gonna make life easier and just say SR for the symbol. I'm gonna need Fe for iron. I'm gonna need chlorine, Cl for chlorine, and then Pb for lead. We're going to need to have some lines here to kind of separate some things out. We're going to need to find, subatomic particles. So let's go protons. Let's go electrons next. It's just going to make life a lot easier for us, I think. You could go neutrons next. But I'm going to go electrons next. I think it'll be easier for us. Let's go neutrons. Okay. Nuclear symbol. If you want an added challenge, if we have some time, maybe we'll do electron configs as well. And if we really have time, Bohr models. May or may not get to those last two. But it is something you should know. First off, strontium-87. So I need to look at my periodic table, find strontium. In finding strontium, I can see that the atomic number is 38. Okay. So that means since the atomic number is 38, the number of protons is also 38. Since we're not dealing with an ion, the number of electrons is also going to be 38. Now, we need to be able to do some simple math. We can either A, do this in our head, or use a handy-dandy calculator. And we know that the atomic mass unit, the AMU for strontium-87, is going to be 87 because that's a whole number. Even though if we looked on our periodic table, it'd be some decimal, but because it's 87, that's going to give us a whole number. I subtract 38, and I will get the atomic, the number of neutrons to be 49. Now the nuclear symbol would be 87. Now, what a lot of times students try to do is they try to write it as a fraction and put a line there. Do not do that. Okay? We are not dividing, and it's not being written as a fraction. Okay? So that's very important that we don't do that. It's very common for students to want to do that. Okay. Moving on to iron. And so for iron, let's look at, say, the atomic number for iron is 26. Because again, we're dealing with a neutral atom. Also, the number of electrons will be 26. The number of neutrons will be 56, since we're dealing with iron 56. Now, if we were dealing with, say, iron 57, then the subtraction would be different. But iron 56 minus 26, so 56 minus 26, gives us 30. The nuclear symbol for iron is 56, 26, Fe. Now, I have seen in years past some students write the nuclear symbol first, then we'll write the number of neutrons, because they have that subtraction set up for them. That's not a bad idea to do as well. For chlorine, looking at my periodic table, I need to find the atomic number for chlorine. That would be 17. So that gives me the number of protons. Since we're dealing with a neutral atom, the number of electrons is also going to be 17. The number, let's do the nuclear symbol first this time. And so the nuclear symbol will be 35, 17, then the Cl. 35 minus 17 is 18. Then it will bring us now to lead, where, let's do that. That'll be fun to do. For lead, we look on the periodic table to find the atomic number of 82. Since it's a neutral atom, also the number of electrons will be 82. The nuclear symbol, or atomic notation, 207, 82, with the formula of Pb. Now I have to do, again, some math. Either you can do it in your head, and this is one of those ones where having a handy-dandy calculator could be helpful, or just really know how to do math in your head to get an answer of 125. All right, so let's go back and let's look at the electron configurations for these. I'm going to use atomic notation for that. And so for strontium, let us go with the nuclear, not the nuclear, but the noble gas configuration, meaning the previous noble gas to strontium is krypton. Now strontium has a little bit more than that than what krypton has, and that would be a 5s2. as well. For iron, let's do the same type of thing and go with the noble gas configuration. For iron, the previous noble gas is argon. Iron has the addition of 4s2, and it is in the D block, and since it's in the first D block, and the D blocks are n minus 1, so it'd be in the 3D, coming right out at you. And since it is in the sixth one, it would have a 3d6. Chlorine, the previous, and now here's a lot of times, some people like to try and just write argon and then write the electron configuration or what kind of the other part for chlorine, but that's not right. You need to have the previous noble gas, and then it has 3s2, 3p5. It is the fifth element in the P block. For lead, things get pretty big, and therefore the previous noble gas is xenon. Lead has the addition of 6s2. Now, what you write next is kind of, well, doesn't bother me none. Whether you write 5d10, 4f14. If you write 6s2, 4f14, I'd be okay with that. 5d10, 4f14, it really doesn't matter. 6p2 would be your next one. Now, Bohr models, I don't know if I'm going to be able to draw things small enough for that. But those, again, a lot of it comes down to how many circles is based on the outer edge. So strontium should have 5 circles. Iron should have 4. Chlorine should have 3. And lead is going to have 6. Lead is going to have 32 dots in the fourth one, not 14, because they're, remember, the noble gas core. Okay. It is also going to have 18 in the fifth ring and only 4 in that outside ring. So that sometimes tends to be a little bit of a confusion when we write out our electron configurations this way. So we can start out with maybe chlorine, which would be a smaller one. 2, 3. And so for that, you would always have to only put 2 in there. And what's going to be nice is a lot of these are going to have these first ones filled. Okay? And then for chlorine, again, we're doing chlorine first, because I think I'm just going to build on it. Is I would have that as my Bohr model, as that would be the next, that next size. And you can kind of see that there's a missing spot right here for that 8th one, because it is one short of having a full valence shell. I'm going to piggyback on this and go straight into the iron. Okay. Iron is going to have 4 in the 4th ring, based on the fact that it's 4s2, but I have to add an additional 6 into this 3rd one, and so I would have to go 1, 2, 3, 4, 5, 6 to make the iron configuration. Well, the next configuration would be for strontium. Now, strontium is going to have a filled, you should have a total of 18, and so I think I have a couple more to add into that there. But it's also going to have 8 in the 4th ring, because that's what krypton would have. But then in the 5th ring, it will also only have 2. Now for lead, things get pretty big. And things get pretty gross. Well, depends on how you want to look at it. So I got 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Now in that 4th ring, I need to have a total of 18 in the 5th ring. Oop, I put too many in the 3. Oh man, that's right there. I guess there becomes a problem right there. Well, we'll fix it after the fact. Let's get some of these other ones in there. So I got 5th ring. I need a total of 10 more. A total of 18 in the 5th ring. 16. There we go. The 4th ring needs to have 32. Come back and go 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, and then 4 in the 6th ring. Now I got to go back in and fix my 3rd. My 3rd should have only 18. In it. And there we go. It's pretty complicated in there, but nevertheless, that's what we would have. Kind of just build it as we went through. So. think that is where we shall end for the day. See you next time.